In this video, we are going to discuss point defects. So, one of the most important point defects is simply a vacancy, and a vacancy is a vacant site in a crystal. So, we make a guess, let us say that there may be some vacant sites in a crystal, because nothing is really going to be perfect in our life, and so some defects can be there. So, there may be some vacant sites, but the real surprising fact is that there must be certain fraction of vacant sites in a crystal, that there is no way we can make a crystal with no sites vacant. That is possible only at absolute 0, and absolute 0, as you know from thermodynamics, itself is unattainable. So, we will see this in detail in this video, why it is so that certain crystal sites have to be vacant. There should be certain concentration of vacancies in equilibrium in a crystal. So, we talk about equilibrium, and by equilibrium here we mean a thermodynamic equilibrium at constant temperature and pressure. So, which means that we should have a minimum Gibbs free energy. So, a crystal with vacancy should lower the free energy in comparison to the perfect crystal. Of course, this lowering cannot continue forever, otherwise all the sites will be all sites can never be vacant, there will be no crystal. So, there will be certain equilibrium concentration which will minimize the free energy of the crystal. So, what is that equilibrium concentration of vacancy? So, we will try to formulate this or try to answer this question. So, since we want to have an equilibrium crystal in equilibrium, so we should try to minimize the Gibbs free energy. So, what is Gibbs free energy? So, we know by the definition Gibbs free energy is H minus T s, where T is the absolute temperature and H is the enthalpy, and enthalpy H itself is defined as E plus P v, where E is the internal energy, P is pressure and V is volume. Then S in the free energy expression, as you know, is entropy. For the current case, the entropy S is best given by the Boltzmann formula S is equal to K log W. This is a statistical relationship given by Boltzmann, where K is the Boltzmann constant and W is the number of microstates corresponding to a given macro state. Let us see what we mean by this, the meaning of W in the number of microstates corresponding to a given macro state. So, vacancy increases enthalpy H of the crystal due to breaking of bonds. So, energy is required to break the bonds. So, in particular I am now currently focusing bonds formed by this central atom, and in this two dimensional example this central atom is forming 4 bonds. Now, if I want to create a vacancy there, I will have to break these bonds. So, let me break these bonds, and by breaking this bond now I can remove the atom. But you can see if I simply remove the atom, the number of atoms is decreasing. This is not going to happen, the number of atoms should be conserved. So, really to create the vacancy I have to remove the atom from its normal place and then place it somewhere else. Now, in this system that somewhere else we will see can be many locations in a real crystal, like it can be the dislocation core. We have already seen in the case of Klein, dislocation Klein, that if atoms go and join the dislocation core, then their location from which they moved will be created vacancy. So, these atoms can join dislocation core, or they can join grain boundary, or if none of these are present, like in the crystal shown here, they can come to the surface. So, I place them on the surface. So, on the surface it will again form a bond. So, although 4 bonds were broken to remove this atom from here, one bond has been regenerated to put it on the surface. So, effectively for this atom 3 bonds are broken. So, certain effective number of bonds have to be broken to create a vacancy in a crystal, and each bond breaking will require certain amount of energy and thus certain amount of enthalpy to be provided to the crystal to make this replacement of atom from its normal location to, let us say, a less favorable location, in this case the surface. So, if we now think that each such creation of vacancy is requiring an enthalpy delta H f, f, the subscript f is for formation. So, enthalpy of formation of a single vacancy is delta H f, and if I am creating n vacancy, then the total enthalpy increase due to the creation of n vacancies, little n vacancies, will be n times delta H f. Of course, we are assuming that n is very small. So, only quite a few sites are vacant, and also they are far apart, such that the number of bonds broken is constant for each vacancy. Now, let us try to see the meaning of W, the number of microstates corresponding to a given macro state. So, I am showing you here, let us see 5 by 5 25 atom crystal, but one site is vacant. So, we really have 24 atoms with one vacancy, but this vacancy can be located here as in this first figure or somewhere else as in the second figure or third figure or fourth figure. So, these are 4 examples of where a single vacancy could have been located in this crystal. Now, if you think in terms of real atoms and atomic positions, that is, if you are thinking really atomistically, then all these configurations are different. But if you think in terms of macroscopic behavior, the thermodynamic behavior of the material, then you do not expect them to be different. Macroscopic properties you do not expect to be different because of the different locations of vacancies in these crystals. For example, they should have the same temperature or they should have the same pressure and the same macroscopic volume. So, none of these macroscopic parameter will change if the vacancy shifts from one location to another location in these systems. So, microscopically, if we think of exact atom positions, then these are 4 different microstates, but macroscopically, thermodynamically, they will behave as a single macrostates. So, I will say that these are 4 different microstates corresponding to the same macro state. So, now we can think of configurational entropy due to vacancy as if there are n number of atoms and we create n vacancies in the crystal, little n vacancies in the crystal, capital N number of atoms and little n number of vacancies, then the total number of sites which we are playing with is n plus n, because vacant site also we are counting as site. So, there are atomic sites, the filled sites capital N, and there are vacant sites, the little n. So, the number of microstates in this case will be in how many ways from n plus capital N plus a small n sites we can find little n sites to put my vacancies. So, this, as you know from mathematics, is n plus n C n or factorial of n plus little n divided by little n factorial capital N factorial. So, this becomes the number of microstates in the presence of vacancies. Now, according to the Boltzmann expression, the entropy S due to this introduction of these little n vacancies in the crystal will be given by the formula delta S is equal to K log W. So, this will be the increase in entropy of the crystal due to the introduction of vacancies. So, I replace the value of W as we have just calculated here into this, and then expand the logarithm to get this final expression. So far so good, but these numbers, the factorials, the argument of the factorial argument of the log n plus n factorial, this is a very large number. We are talking of atomistic system. So, even a mole Avogadro number of atoms will be 10 to the power 23 atoms. So, this will be a very large number. So, there is a process to simplify finding logarithm of large factorials, and that will come to be very useful for us. So, we will look at that approximation, that mathematical approximation given by Stirling, known as Stirling's approximation, and that is log of factorial n for large n, it is simply n log n minus n. So, here you can see that here we have to find first the factorial of a large number and then take the log. Here that finding factorial has been removed, you have to simply take log of n multiply by n minus n. Mathematically this simplifies the process very much. For example, if you now let us see how good is this approximation. So, let us begin with the first column I am making of n, and then second column is the exact value log n factorial, and the third column is the approximate value n log n minus n. Let me begin with a very small number, just 1. So, for 1 log factorial n is 0 and n log n minus n is minus n. So, this is quite different and one can see that difference, but anyway the approximation is for large n. So, at the moment we have not reached that large limit and approximation is not good. But even if we go to 10, we start finding that it is becoming a good approximation. Now, log factorial n exact value was about 15, whereas the approximation is giving a value of 13. So, we are making an error of 2 in 15, which is still 12-13% error. But if you go to 100, now the exact value comes to 363, the approximation is only 360. So, now the error is only 3 in 360, it is less than 1%. So, even for 100 the approximation is within 1% to the actual value, and as we go to larger and larger value, you will find that actually the difference saturates to about 3. So, a difference of 3 will be coming in a much larger value, Avogadro number of atoms for example, if you go to, this will be a very large number and the error will hardly be perceivable. So, Stirling's approximation is a very good approximation for large n, and you will appreciate the mathematical simplicity if you really try to calculate this number log factorial n. For that, first you have to calculate factorial n, and factorial n itself is an extremely huge number. Here by Mathematica I have calculated and showing you 100 factorial up to the last digit, and you can see it is a really huge number. So, first calculating the factorial will become very huge task, and then you have to take logarithm of this large number, whereas in this case we will take only log of 100 and multiply it by 100 and subtract 100. So, you will get 360. So, by much less work you are getting a very good approximation. So, let us now use this Stirling's approximation into our work. We have already seen that we have come to this expression for increase in entropy due to introduction of little n vacancies in a crystal composed of capital N atoms. Now, we have this Stirling's approximation and we apply the Stirling's approximation to this expression to simplify it to this form. Now, there are no factorials, I have simply capital N plus small n log capital N plus small n minus small n log n minus capital N log capital N. So, we have a simplified expression for the entropy increase due to the introduction of a small n number of vacancies in capital N at number of atoms. And we also have an expression for enthalpy. So, now we have the two components which we require for our free energy, the enthalpy increase and the entropy increase. So, if we put these two together with the temperature, we will get the change in free energy of the crystal. So, let us do that graphically. So, on the x axis I have the number of vacancies and on the y axis the change in free energy, but we will do it in steps. Now, if n is 0, if there are no vacancies, so that is our perfect crystal. So, the perfect crystal is sitting at the origin here. Now, our increase in enthalpy was simply n times delta Hf. So, and since n is our x axis, it is simply a straight line with delta Hf as its slope. So, we have a straight line for enthalpy. But if you plot the entropy change, which was this logarithmic expression which we derived, and minus T times delta S, because that is what goes in making delta G, then you have a curve like this. Because of this minus sign, this curve is a negative curve and you have this. The sum of these two, delta H and minus T delta S, will be delta G. So, you can add these two. You can see that initially this delta S curve has a very high slope and then gradually the slope decreases, whereas the delta H curve has a constant slope. So, initially minus T s term will be dominant and the delta G curve will come down, but gradually as its slope decreases and this keeps growing at a constant rate. So, delta H will start becoming dominant and the curve will come up. So, if you plot this curve, you get something like this. The red curve now is the sum of this blue curve and the black curve. Delta G is sum of delta H minus T delta S. So, I have this free energy curve. Once you have this free energy curve, you now realize that this is showing a minimum at certain number of vacancies. So, that means this number of vacancy where you have this minimum in the curve is the equilibrium number of vacancy which this crystal will accept, which this crystal will be happy with. So, that particular vacancy number I now label as N equilibrium. So, N EQ, N equilibrium is the number of vacancies at which the free energy of the crystal at this temperature is minimum. So, then equilibrium concentration of vacancy is easy to find. All you have to do is start with your expression of delta S and delta H and construct your delta G, which we have already done graphically, and then differentiate this expression, because at equilibrium this delta G is minimum. So, del of delta G by del N will be equal to 0. The slope of the curve at the minimum point will be 0. So, if we simply differentiate this expression, I leave this algebra for you, please do that. So, simply differentiate this expression and apply this condition, then you will find what is the equilibrium number of vacancies, and here I am showing it as a ratio to the total number of atoms. So, equilibrium number of vacancies divided by total number of atoms is equal to exponential of minus delta Hf by kT. In getting this final expression in your algebra, you will have to apply this this approximation that the equilibrium concentration of vacancy is much smaller than the number of atoms. So, this is the final expression which we were looking for, and this is what answers our original question, that what is the equilibrium concentration of vacancy. This ratio is what we are calling the equilibrium concentration of vacancy, and that is an exponential function, exponential minus delta Hf by kT. Recall that delta Hf was enthalpy of formation of one vacancy, K is Boltzmann constant and T is temperature. Let us look at some values. So, aluminum has an enthalpy of formation of 0.70 electron volt per vacancy, and delta Hf is 1.74 electron volt per vacancy for nickel. So, nickel has enthalpy of formation of vacancy about 2 times more than that of aluminum, more than 2 times. So, you can see aluminum has a weaker bonding, has a lower melting point. So, has a lower enthalpy of formation because bonds are weaker. Lower melting point means bonds are weaker, and remember enthalpy of formation was nothing but enthalpy for breaking the bonds to create the vacancy. So, since the bond energies are less in aluminum, the corresponding enthalpy for formation of vacancy is also smaller. Similarly, in nickel is a high melting point material. So, the bonds are very strong, and to break those stronger bonds you will have to provide more energy. So, enthalpy of formation of vacancy is higher in nickel. Now, if you use this expression to calculate for 0 Kelvin, of course, if T is 0, the argument is infinity and exponential of minus infinity will always be 0. So, whether it is aluminum or nickel, there is 0 concentration of vacancy at absolute 0. But at all other temperature, there will be certain fraction of sites which will be vacant, and these are the fractions shown here. But you can see that at most reasonable temperature, at the room temperature for example, aluminum has only 1 in about 10 to the power 12 sites vacant. And similarly, this will have about 5 in 10 to the power 30 sites vacant. So, this vacancy concentration is really very small at low temperature, but because of the exponential relationship, and it depends upon the material, and there are several orders of magnitude difference in the vacancy concentration of nickel and aluminum. Aluminum has much larger number of vacancies at room temperature than nickel has. But as you start heating, and at 900 Kelvin, you have in aluminum about 1 site in 10 to the power 4 vacant. So, in 10,000 sites there is 1 vacancy. Now, the vacancy concentration, this is a very high vacancy concentration. Aluminum at 900 Kelvin is very close to its melting point. So, close to the melting point, vacancy concentration becomes quite high, whereas nickel is still far away from its melting point. So, although the vacancy concentration has gone several orders of magnitude higher at 900 K, but it is still much lower than its melting, the temperature is still much lower than its melting point. So, it can go still higher values like 10 to the power minus 4 as this also starts reaching its melting point. In fact, one theory of melting is that the vacancy concentration becomes so high that the crystal is no more able to support itself and just collapses. So, you get melting. This slide just tries to clarify one confusion, that sometimes the expression is written with K and sometimes the expression is written with R. The difference is both are correct expression, but the interpretation for delta Hf changes. If I write it with K as I was doing it till now, then it is enthalpy of formation of a single vacancy. That is why I recall that I wrote for aluminum and nickel, when I was writing the value, I was writing electron volts per vacancy. So, it is for one vacancy, then you use Boltzmann constant. But of course, if you multiply both numerator and denominator here by Avogadro number, then delta HF will change to enthalpy of formation of a mole of vacancy, whereas Avogadro number times Boltzmann constant will become gas constant R. So, there is really both are the same expression given differently, one with delta HF by KT, another with delta HF by RT, but we have to be careful about the unit or the interpretation of delta HF. If it is K, it is enthalpy of formation of a single vacancy, and if it is R in the denominator, then delta HF is enthalpy of formation of a mole of vacancies. With this, we end our discussion on vacancy, but let us discuss a few more kinds of defect, or rather let us first discuss one interesting effect of a vacancy to thermal expansion of the crystal. This is very interesting, and this is one way by which this delta HF can be experimentally determined. So, let us do that. So, increase in vacancy concentration increases the volume of a crystal. So, vacancy actually contributes to the expansion. How does that happen? Let us see. You remember the diagram which we made, where we said that if we create a vacancy, the atom has to be put on the surface. So, if I put it on the surface there, then I have added one site on the surface. So, I have added an extra volume to the crystal. Initially, the volume was limited by this square boundary in this two dimensional example, but now here the boundary has expanded to include this atom. So, the overall volume of the crystal has increased. So, a vacancy adds a volume equal to the volume associated with an atom to the volume of the crystal. You can think of this system now. You can see there are 3, 4, 5, 6, 7, and then 3, 6 and 7. This is a 7 by 7 square which I have made. So, it is 49. There was supposed to be 14, there is 49 atoms here, but there is one vacant site. So, now total number of sites is 50, and the vacant site is also occupying the same volume as the occupied site. So, although there are only 49 atoms, 7 into 7 49 atoms, I have a volume corresponding to 50 atoms, because there is one vacant site. So, every vacancy adds volume equal to the volume associated with an atom to the volume of the crystal. Thus, vacancy makes a small contribution to thermal expansion of a crystal. Thus, the total thermal expansion we can write as two components. One is because of the lattice parameter expansion. So, of course, when you are heating the crystal, the bond length also is changing, atom to atom distance is changing. So, there is an increase, in the bond length. So, that is the lattice parameter expansion, and the other one is increase in volume, as we just discussed, due to vacancy. So, if we write the total volume of the crystal as total number of sites times the volume per site. So, V is the total volume of the crystal, little v is volume associated with one atom, and N is the total number of sites. So, it is atom plus vacancy. We are assuming that vacancy is also occupying the same volume as atom. So, the total volume of the crystal will be N times V. If we simply differentiate this expression, then delta V will be capital N times delta small v plus capital V times delta capital N. So, we get this expression by simply differentiating, and if I divide this by the original expression V is equal to N V, we can write in terms of fraction. So, total fractional increase in volume is this fraction, the first fraction plus the second fraction. If you look at the the left hand side is of course the total expansion, but on the right hand side the first fraction will correspond to lattice parameter increase, because this little v is the volume associated with one atom. So, and how the volume per atom will increase? The volume per atom will increase only if the lattice parameter increases. You recall that every unit cell has certain fixed number of atoms. So, if we have body centered cubic crystal, then in the body centered cubic crystal there will be 2 atoms per lattice point, 2 atoms per unit cell. So, if the lattice parameter increases, then the 2 atoms per unit volume will decrease. The number of atoms per unit volume will decrease, or the volume per atom will increase. So, this is the increase in volume per atom due to lattice parameter increase. Now, the second term, the delta n by n, is because of the increase in the number of sites. How the number of sites can increase? The number of atoms is fixed, number of atoms are conserved. So, the total number of sites will change only if there are more vacancies getting added to the system. So, this delta n is nothing but the number of vacancies. So, the second term is coming from vacancy contribution. So, if we write like this delta v in our expression, the fractional increase, and then I am changing it to from volume increase to length increase, and you know from your basic physics that the fractional change in volume is 3 times the fractional change in length in case of thermal expansion. So, the first one on the LHS I changed it to 3 times delta L by L, fractional changing length. Delta V by V is due to the volume change of the crystal due to lattice parameter increase. So, this is 3 times delta A by A, where A is the lattice parameter. And here we have already said that this delta n, the change in the number of sites, has to be due to the addition of vacancies, and since we have added little n vacancies, so for delta n capital N I am writing this is small n for number of vacancies. You can now write rearrange this into this form, where now this n by n, which was my vacancy concentration, I have written on the left hand side and the other terms on the right. If you do careful experiments, both the terms on the right hand side can be measured. So, delta L by L is the linear thermal expansion coefficient. Well, it is not a linear thermal expansion coefficient, it is due to the linear thermal expansion, and you can find that by thermal expansion experiments. And this delta A by A is the lattice parameter change, and if you do X-ray diffraction as a function of temperature, you can measure what is the change in the lattice parameter as a function of temperature. So, you can find delta A by A. So, you will then get the fraction of vacant sites in your crystal. So, if this fraction of vacant site is measured as a function of temperature, you can then use your equilibrium concentration formula to find delta HF. So, this is one way of getting delta HF. So, we have talked about point defects, but the only point defect which we have mentioned till now is the vacant site. So, there is a vacancy which is missing of an atom, but then there are other kinds of point defects. So, for example, there may be an interstitial impurity. By this is L coming from here. So, interstitial impurity, and this is an atom which is sitting on a some sort of void or interstice of the crystal. So, this red atom is an interstitial impurity, but this blue atom is sitting at a location where black atom should have been sitting. So, this is a substitutional impurity. You have met it in interstitial and substitutional solid solution when we discussed that topic. So, now we are looking these atoms which are located either in the interstice or located at the atomic site, but is a different atom, as point defects. So, they are interstitial and substitutional point defects. In ionic crystal, we have two more varieties of defects which can be there. So, here I am showing a schematic of an ionic crystal. So, you can think of the larger one as anion and this smaller red one as cation. So, various kinds of point defects are possible in such ionic solid. So, for example, there is one which is called Frenkel defect. This defect is created if a cation is moved from its normal location to some other interstitial site in the crystal. So, you actually have a pair of pair of defects together. There is a cation vacancy as well as a cation interstitial. A simple cation vacancy or a simple anion vacancy is not possible, because that will lead to charge imbalance in the crystal, and thus the energy of the such crystal will be much higher because of the charge imbalance. So, they are not seen, but Frenkel defect, in which a cation is simply misplaced from its site to some other interstitial site, creating a cation interstitial and a cation vacancy. This is known as Frenkel defect. The other kind of defect is a Schottky defect. In this, you create a pair of vacant site. Again, simple anion vacancy or simple cation vacancy is not possible, but it is possible that the whole pair, a cation anion pair, is missing from the regular site. So, this kind of defect is called Schottky defect. So, this completes the discussion on point defect. We will go to discussing line defects in future videos.